Hello, welcome to Solidio Gloria Physical Chemistry. This is the lecture for Physical Chemistry, Part 1, Thermodynamics. Well, actually this is prepared for a summary of thermodynamics. Basically we are going to talk about basics or introductory part of thermodynamics. So the subtitle is State Functions. So let's begin. Well, before I do that, let me talk to you about what would be the best for you. Is that this lecture is intended to be short, but I don't intend to be very long, make a long lecture, but it may take about an hour. Korean version did that. So, but you basically, this is really basic idea. The essence of thermodynamics. So watch, repeat many times, and then make a note, and then memorize it. It's a memory work. So basically, this is for your memory work. Okay. So let's begin. So this is about the state functions. Okay. You see this picture? This is the chemistry man. Chemistry man juggles matter and energy. He's trying to deal with universe. Okay, so basically the thermodynamics is quantitative relationship. He's dealing with quantitative relationship between thermal and mechanical energy. So thermodynamics. Thermodynamics deals with properties of macroscopic system at equilibrium and measure the changes. So change in kind of the state of the system, we call it process. He's observing the process and try to figure out what's going on in the universe. But he's a limited human, not maybe chemistry man, is limited being. And then he's limited, then he is not really able to deal with the entire universe, so he has to confine his interest into something, a part of the universe, which is a system. System is a part of the physical universe under consideration, and system is a part of the universe. Then rest of the universe, except the system, is the surroundings. And then you just imagine that system and the surrounding make the universe. Okay, so thermodynamics is based on the observation of the system itself, and it's just to keep concentrated on macroscopic behavior of matter, and from that he projects out what's going on in the universe. So observation is on the macroscopic behavior of matter within the system and establish the law of thermodynamics. Law of thermodynamics encompasses zeroth law, first law, second law, and third law. Okay, so then basically try to pinpoint or denote the state of the system. State of the system. Let me get the laser pointer. I don't know how to do that. Okay. Anyhow, so basically we are doing concentrate on the system and try to find out what's going on in the system and the surrounding in the universe, and we denote the state, what's on the system, state of the system, by the state function. Sometimes we call the state function as state variable, because in the mathematics we usually deal with the functional relationship among variables like dependent variable and independent variable. Independent variable obviously is the state, and state variables. Okay, independent variables are state variables, and dependent variable is a state itself. But here we just say state function, which is a state variable also, because once a state variable is fixed, it tells what the state it is, and also that state variable itself is kind of expressed by other state variables. So all are state functions in some sense. In a way, the dependent variable is there, but independent variable is there, but we can reverse reciprocal relationship is there. So anyhow, state is denoted, state of a system is denoted by state variables, and we can surely tell that state variable is also state function. So we will use just one term, state function, that state the state of the system. So first we'll talk about the Zeroth law of thermodynamics. So essence of the Zeroth law of thermodynamics is to tell you there is a state function that denotes the state of the system, which tells you about the thermal state. Then that is the variable or state function, temperature. It is actually done in such a way that I'd like to get some laser pointer. I'm not sure how do I get it, but let's do it this way. Okay, yeah, I got it. So the Zeroth law of thermodynamics is in such a way that there are systems under our concern, and then system A and system C make a thermal contact, which means thermal contact means that contact allows the heat transfer of heat. Then that's the thermal contact. A and C make a thermal contact, and then there is no change, meaning is thermal equilibrium. If there is a change, like heat flow against the temperature gradient, meaning is that some state to another state, there is a kind of difference in thermal state. So heat flows from state A to state B, something like that. So state C in this case. So there is not such a thing. So A and C, state A and state C make a thermal contact. There is no change in thermal state, meaning is that there is no heat flow. Okay, then we say that state A and state C make a thermal equilibrium, and then state A and state B also make a thermal equilibrium. Then what? We can tell for sure, absolutely, state B and state C make a thermal equilibrium. So I'll just read this. If system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with system C, then system A and B are in thermal equilibrium with each other. Well, actually, this statement is kind of, these figures are kind of mixed up, but anyhow, that's what it is. That's what it is. Okay, so this Zeroth law of thermodynamics is telling you what? There is something that denote equilibrium state among systems, thermal equilibrium state among systems. What would it be? That is a temperature. So temperature is the state function of a system denoting the thermal state, which means that if the temperature of A and temperature of C are the same, and if temperature of A and temperature of C are the same, then we can for sure, definitely can say that temperature B and temperatures of C are the same. Okay? So temperature is a state function that denotes the thermal state of the system. And then there are temperature scale. Actually, this is a kind of advanced or summary lecture. So I'm just going to tell you about the conclusion itself. So there is there are Celsius and Fahrenheit and Kelvin scale. Kelvin scale is the absolute temperature scale, and then in the 1 Kelvin is 1 K, which is exactly the same as Celsius scale 1 degree C. And then there is a relationship between Celsius and Kelvin or absolute temperature scale. So if you add 273.15 to centigrade, then you will get the absolute temperature or Kelvin scale. What is behind of this is that there is a triple point of water at normal, which is 1 atm pressure, which is as temperature is concerned, which is 0.01 degrees Celsius, which we define as 273.16 K. Remember that absolute temperature scale we don't use degree sign, so Kelvin is the unit. And then normal melting point of water, ice at normal pressure, which is atmospheric pressure, is 273.15 K. So you just add 273.15 to the absolute the Celsius temperature, then you will get the absolute temperature. That's the relationship. That is the relationship. Okay, now, so we are trying to dig out what are those those state functions. So we have now two. First one is the volume. Volume is absolute concept in a way that volume you don't really derive from anything else. Volume is given. So volume is a state function. Volume is denoting the state of a system. And then by the zeroth law of the thermodynamics, we just established the second in our list state function, which is temperature. And then third one is pressure. Pressure in physics or mechanics, we define it as force per unit area. Normal 1 atm or atmospheric pressure is kind of established or defined by 76 centimeters of mercury column, you see, at 0 degrees Celsius. And then at the 0 degrees Celsius, its density is 13.5951 times 10 to the third kilogram per meter cube. And then we multiply that, that's the mass, mgh. G is the gravitational constant, which is 9.80665 meter per sec square. And then 76 centimeters is 0.76 meter. So all these together, you will end up with Newton per meter square, which is Pascal. Then the number is 101,325 Newton per meter square, which is 101,325 Pascal. That is 1.01325 bar actually. So this is a kind of definition for the 1 atm and the bar. So we use pressure unit Pascal, bar, atm, or torricelli, or millimeter mercury, like that. And then these are the relationship. And then another kind of one audible here is that PSI. PSI stands for the pound per square inch. In America, in the United States, they use this unit for just ordinary life in a way that, for example, if you have an automobile vehicle to drive, it's a passenger vehicle like a sedan, and then normally I remember that it's like 32 psi, which 1 atm atmospheric pressure is 14.696 psi, pound per square inch. 32 means that it's a little bit more than 2 atm. So that's the air pressure of your tire of the vehicle, something like that. Okay, so we now have three state functions: volume, temperature, and pressure. Now what's going on? Okay, once we have these three state functions, then we are ready to deal with the state of a gas phase. So gas phase has, we can define the volume, and we can say what's the pressure of it or temperature of it. Then we know the state. And actually the relationship among these three state variables is an equation of state. For example, for an ideal gas, which is PV equals P times V equals N RT. You see, that's kind of T V P relationship. So at STP stands for the standard temperature and pressure, and then when we are talking about gas phase, and then which is 0 degrees centigrade or 273.15 Kelvin and 1 atm pressure, the molar volume of 1 mole of gas, ideal gas, is 22.414 liter. Then there is a relationship PV equal nRT. Then R is the gas constant, and we assume 1 mole of gas which occupies 22.414. Well, I use the laser pointer. 2.414 liter, and then 1 atm pressure, and then 0 centigrade, 273.15 K, and then these numbers altogether yields you 0.082058, and then we collect all the unit there, liter atm per mole K. Okay, so this is a gas constant. Okay, that's a constant. So this is based on 0 degrees Celsius and 1 atm and the volume of an ideal gas. But there is no such a thing, ideal gas, you know. So we use kind of technique to figure out what's the volume of it. And then, but for the more accurate measurement, we rely on some other thermodynamic or physical quantity, which is the sound of speed of sound in a media. In this case, they used argon, which is very kind of recent than development of thermodynamics for early days, which is 1986. People measured the speed of sound in argon and then made a relationship or model, and then figured out the better accurate gas constant, which is this number here. Well, actually you see that liter atm y is concerned, that corresponds to, from the speed of sound of argon, 0.08205 instead of 8 is 7 liter atm per mole K. You see, liter atm could be converted to joule. 1 liter atm is actually 1 liter atm is 101 about joule. So anyhow, there is a relationship. We'll derive that later in a couple of slides. So which corresponds to 8.31451 joule per mole K. You see, just 100 times, like roughly. And then you see 1 calorie is 4.184 joule. So then you have this relationship. So R, there are kind of joule per mole K, calorie per mole K, liter atm per mole K. So 8.31451, 1.98722, and 0.082057. These are all gas constant with different unit. So just to know it and then use properly for a given problem. Okay, now we are at the point to define what is work and what is energy. Just to retrospect, we say that we check that we have now volume, temperature, and pressure, state functions. And then we'll define what is work and what is work and heat. And then unfortunately we'll end up with that those are not. Those change the state. So those are involved in the process. Process is a change in the state. And then, but those are not the state functions. And then we need a state function that encompass or include work and heat that denote the state of a system. Okay, so let's first do the work. Work is a energy transfer through the mechanical link between the system and the surrounding. Okay, so system and surroundings there, and then system does work to the surrounding or accept the work from the surrounding. So that's the idea here. So work is what? Energy transfer between the system and the surrounding through the mechanical link. Okay, so that is work. Work normally in your early physics days is defined as force kind of times the distance. Okay, so force times the distance. Actually, those are vector quantities, so it's a dot product. But anyhow, this is force times the distance. If you divide the force by the area and area multiplied to the distance, then you have force per area is pressure and area times the distance is volume. In this case, you have a piston. There is a pressure P exerted on top of piston, and then the volume was there, and then the volume increases, meaning is that expansion was there against the pressure P, and then the volume difference is delta V. Okay, so delta V times this P gives you the amount of work. But the system, the yellow part within the piston, and then expand, which means that this system does work to the surrounding, and then we define the sign in such a way that if anything comes into the system, that's positive, comes out of the system, that's negative. So in this case, that comes out of the negative, but this delta B is positive, pressure is always positive. Then you see this positive times positive, positive, then that quantity work, because system does the work, and that work must be negative, so we need a sign negative here in front of this number. And then we just in the previous slide I just told you that 1 liter ATM is 101.325 joule. Well, this is the relationship. Well, actually liter is not a SI unit, ATM is not a SI unit, System International Unit. So standard unit requires the liter to the meter cube and ATM to the Newton per meter square, which is Pascal. So we do this arithmetic or calculation, and then we get this 101.325 joule, 101.325. So 1 liter ATM is roughly 1 joule, 100 joule. I'm sorry. Yeah. So that's what it's telling you about. Yeah. Okay, so once we know the work is the energy transfer between the system and the surrounding through the mechanical link, then let's find out what is heat. Heat is, conclusively, I will just tell you, thermal energy transfer in thermal contact, of course, between the surrounding and the system through the temperature gradient. So if two systems or system and the surrounding make a thermal contact, and then there is a temperature gradient, then heat flows. So heat flow, heat flow, I mean heat energy transfers. Okay, so heat is thermal energy transfer in thermal contact through the temperature gradient. That's how we define the heat. Well, actually there is a idea, it's very old idea of Joule. He demonstrates that mechanical equivalence of heat to work. So he claims that work and heat are equivalent. Well, this is a kind of schematic diagram of his apparatus, but anyhow, he dropped the weight, and then he can actually exactly measure amount of work done, and then that work done is transferred by kind of mechanical link to the pedal, and then pedal does work to the system, which is water contained in this insulated area, and then that erases the temperature of the system. Work erases the temperature of the system, and then people can accurately measure the amount of heat, heat by heating it, that required to raise the same amount of temperature. So what is how they measure the heat amount of heat is by the unit of calorie. 1 calorie is defined by the amount of heat that raises 1 degree of Celsius in that case from 14.5 degrees centigrade to 15.5 degrees centigrade. So that is the heat amount corresponds to 1 calorie. And then by doing this experiment, Joule determine which is 4.184 joule. So 4.184 joule of work is equivalent to 1.0 calorie of heat, and then those are equivalent. So heat and work are kind of same thing, denoting the change or progress of the system. Okay, so before we go on, we'll just summarize that, or just to check we know about it. What is work? Work is energy transfer between the system and the surrounding through the mechanical link. Okay, that's a kind of phenomena, which is path function, how it is done. And also heat is the thermal energy transfer in thermal contact through the temperature gradient. So basically we know what those are. Those are phenomena, not state function. Heat itself or work itself do not denote the state of a system, but together they will do. So let's do the first work of thermodynamics. So there is a system and surroundings and system boundary. Something cross the boundary, which is work or which is heat. Heat is added or heat is removed from the system, or work is done, or system itself does the work. By doing so, it changes its state, meaning is that there is a process. The process involves heat and work. So firstly, if there is no heat transfer, which is a system adiabatic process, thus adiabatic process, in that case whole change is done by work. So the change in the state, progress is adiabatic in this case, and then that process is denoted or expressed only by work. So delta U, well actually it's a little bit early to use this symbol, but anyhow, the change in the system or progress of the system, process of the system is expressed only by work. And also, if there is no work done, how you say or how you are sure there is no work done? Meaning is then when you fix the volume, delta V equals 0, then there is no pressure volume work because delta V equals 0. So you fix the volume, then there is no work done. Then there is no work, then if system changes state, meaning that there is a process, then there must be heat is involved in that process. Okay, then heat absorbed by a closed system in a process, there is no work done, and then that is equal to the change, equal to something that denotes the change or that denotes the final state of the system compared to the initial state of the system. Okay, that is done by only heat, right? So now we just talk about there is a change in the state A to state B change by work, state A to the same state B change by heat. So either heat or work can change or do the process of the system. Then maybe you can just mix them in a way, halfway done by heat or halfway done by work. Still you do the same change from state A to state B. Okay, that's what it is. Then there must be something to denote the state, which is thermal and mechanical state, or heat and work state. And there is such a thing. They are together. Just alone, heat alone or work alone could not define the state, but their sum, heat plus work, the sum Q plus W will denote the state of the system. Okay, then that's a state function. Q plus W is a state function in this case. But obviously, you just assume that there is only heat transfer for the thermal energy, and for the mechanical work-wise concern, you just assume pressure volume work. Okay, anyhow, then anyhow, the state of a system is defined or determined by the amount of work and amount of heat involved in the change of state. Okay, so now then we are going to ask you then, what would be the state function that denote that thermal and mechanical state? And then the answer is the first law of thermodynamics, which tells you or state by in such a way that the energy of the universe is the same. Okay, the energy of the universe is constant. Okay, so that is the energy change, delta U. That something, the state function, change in the state function is equal to Q plus W, heat plus energy, heat plus work. Okay, so then the question is, what would you call the name of the state function? That is energy. Okay, so the energy, in this case that we use the symbol U, delta U is defined as Q plus W. So heat plus energy, heat plus work define a state function. We call that state function internal energy, or just the energy. So delta U is equal to Q plus W. And then it's something like that. You start from here and then go there and go back to the same point. Then that's a kind of you integrate the path, meaning is that a cyclic path. So you begin here, go somewhere and go back to the same point. Then there is no change in the state, right? You just go back to the same state. Then that amount in the change in the state function is zero. That in this case, a cyclic integral of a state function, that is zero. Okay, either way, delta U equals, in a way, that state from state 1 to state 2, then U2 minus U1. Delta U equals U2 minus U1, or cyclic path, integral du equals 0, which means that U is a state function. Okay, so that's the way we can say something U, in this case, is a state function. So first law defines a state function energy, which is the sum of heat and work. Okay, so energy, in this case, what we have here now, we have volume, absolutely given concept, volume, temperature, pressure, and now we have energy. Then we can express the energy in terms of other state function. In this case, we have T and V. So U is a state function of T and V. Then a differential of U, which is du, is equal to, actually there are two independent variables, then we use partial derivative, more than two variables. So round U round T V, du dt, if you say du dt, which is an ordinary different derivative, partial derivative we use round instead. So round U round TV dt, round U round Vt dv. So this is a formal differential of du, and then du, U is equal to Q plus W. So du is dq plus dw. And then you see bar here, actually this is not really bar, because I don't have font like that. Usually this is a cross here. Okay, so this is not a derivative independent path, but this is path dependent derivative. That's what it says. Okay, so that's what it says. Okay, anyhow, so anyhow, this is d bar dq, d bar q plus d bar w, which is du, right? Okay, so but dW itself is minus P external and dV. Okay, dQ P minus P dV. P dV, yes. So this and that and this part, I'm sorry, equated, this and this part equated, and we'll rearrange it for dq. So dq is this one here, and then minus this dq is here, move to this side. Okay, so and then minus to the positive, and then just this one. Okay, so we have this relationship. Okay, d bar q equals round u round tv dt plus dv here, p external plus round u round vt. So just to kind of keep this in your mind or in your head, whichever, and then we'll go on. Okay, so this is it. And then at the constant volume, and then we just disregard this one, and then you see, then what you have here, and dt dq. So you divide dq by dt, then this is it. dq by dt, dq over dt is that heat over temperature, meaning is that you need some amount of heat to raise the temperature by unit temperature. Yeah, so we call that is a heat capacity, in this case Cb, because it's a volume constant, volume fixed. Okay, so dq is Cv dt, or round u round t, which is Cv dt. Okay, so that's the relationship. So you have a function of C, heat capacity, then you integrate from T1 to T2 and obtain the amount of Q. Okay, amount of Q, just like that. Okay, so we talked about the energy now. And then I'm sorry, excuse me. And then we are at the position to talk about enthalpy. Okay, so up to now, just check the list. We have volume, temperature, pressure, and energy. Now we are going to talk about enthalpy. You see, delta U, which is internal energy, is Q plus W. But let's assume that pressure constant, then QP is, and Q is QP, pressure constant Q. Okay, then QP, we use W as PdW. I'm sorry, P delta V. And then you see, this is a because pressure constant, we can use just P instead of P external. Just P QP minus PdW is for delta U. And then P is a constant, delta V is V2 minus V1, and delta U is U2 minus U1, because these are U is a state function and V is a state function. So we can just express the delta as 2 minus 1, delta 2 minus 1, like that. So if we rearrange this two together, one together, just like that, so QP is equal to U2 plus PV2 and U1 plus PV1. The form of this is that state function plus state function times state function, then which is state function. Then what would you call it? Or whatever it is, we used a sign H and then named it enthalpy. So enthalpy H is defined in such a way that H equals U plus PV. Then QP is H2 minus H1, just like this. Okay, and d bar QP is equal to dH. Right. So now this H we use to, now we have VTP EH. So now we use, because this QP will determine H, then we use two variables, which is T and P. So we assume that h is a function of t and p, then we can do the differential for dh, round h round t p dt, round h round p t dp. And then if there's a pressure constant case, then dp equals 0. And then this one, dh round h round tp is what? Which is heat capacity, but in this case is pressure constant heat capacity. So dqp, d bar qp is cp dt. Okay, that's the same relationship we learned about du equals cp dt. Okay, so now we have volume, temperature, pressure, internal energy, enthalpy. And and up to now we have done first law of thermodynamics, and then now we are going to do second law of thermodynamics, which is just here. So now at this point we are considering an ideal gas, and which is heated reversibly. Okay, that's the condition of the process. Then we do du equal, du is in this case ideal gas heated reversibly. So anyhow, du is cvdt, but which is dq reversible plus dw. Okay, and dq, okay, because this is done, the process is done reversibly, and then dq reversible dw is minus pdv, and then dq minus, because this is ideal gas, then p itself is minus p itself is v nRT over v, pv equal nRT, which is from there, and dv. So this is the relationship. So du is given this relationship, and then we know the dq reversible is cv dt. Okay, so dq reversible is cv dt, and okay, I'm sorry, dq is cv dt. You move this the other side, and then plus nRT over v dv. So this is the relationship we obtain for reversible heat, diminutive value, differential of heat in terms of T and V. Okay, so this is the relationship. Okay, so Q is not a state function, and then the derivative of Q is inexact differential. And then you see, differential of a state function is exact. That's Euler criteria, right? So this is a path function, which is not a state function. Q is. So this one is inexact. So that is inexact differential. How do we know? Because if we make a derivative of CV against V, or derivative nRT over V against T, those two are not the same. So round CV dV, V is not a function of V, CV is not a function of V, equals 0, and nRT over V derived by dt. So round nRT over V round T, and then you just remove this T, nR over V. So 0 is not equal to nR over V. So this is inexact differential. And then when you have an inexact differential, if you find an integrating factor, multiply it to the inexact differential, you will obtain exact differential. So integrating factor in this case is 1 over t. So you multiply 1 over t to dq, then you got dq over t, and then cv over t dt, you see, and nRT over v over t, t is a kind of cancel, so nR over v and dv. So this is it. So in this case, this is a exact differential. So dq over t is an exact differential, and that's the differential of a state function. Meaning is that dq over t is a state function, a derivative of differential of a state function, which is that q over t is a state function. That's what it means. So then what would you call that state function? I would say entropy. And what would give it a symbol? I would say S, because everybody does. So anyhow, so how do you confirm that? So Cv over T derived by V, meaning is that round Cv over T, round V, Cv over T does not have a variable T, so equals 0, and Nr over V derived by dt, D, so round Nr over V, round T equals 0. So are the same, those two are the same, then dq over T is a exact differential, that is the differential of state function, meaning is that ds equal round q over V over T. And this is a differential of a state function. S is a state function, and we named it entropy. Now, entropy, people say that entropy is a kind of order of, I don't know, degree of disorder, something like that. That does not really give you an idea. That does not give you an idea. That's kind of misleading concept. So, entropy entails heat transfer. Entropy entails the change in the state. Of course, the state might be disordered or something like that, but that's the kind of image or just outcome of it. So entropy is a state function, denote that the state of the system. Okay, so what is entropy? Entropy is a state function. That's more that's the kind of true straightforward answer to the question, what is entropy? So entropy is a state function. Now, we are now defined what? Volume, temperature, pressure, energy, enthalpy, and entropy. Now we have 6 and plus 1, which is amount of matter, which is mole, 7 state functions. So we need 2 more to go. So before we do that, we'll combine the first law of thermodynamics and the second law of thermodynamics, and then those two yield you fundamental equation. Okay, so du equals dq plus dw, because u equals to q plus w. That is the kind of direct statement of the first law of thermodynamics. The energy of the universe is constant. Okay, and then second law of thermodynamics was ds equal to dq reversible over t. But if not reversible, which is always greater than ds is always greater than dq over t when it's not reversible. This inequality is Clausius inequality. That is for the second law of thermodynamics. The entropy S of the universe increases. Okay, does not increase, which means that it's in equilibrium. So for a closed system with only reversible PV work, then we say that dW is equal to minus PdV. Because it's reversible, we can use P instead of P external, and then dQ, which is reversible, was that dq over t is equal to ds. So dq is tds and dw is minus pdv. So dq plus dw is what? du. So du is dq plus dw. du equals tds minus pdv. So this, you see, then u, a state function, energy, is expressed by other state functions only. No w and q, which are past functions. So u is was expressed by state functions, and then this is the fundamental equation. Okay, so du is equal to tds minus pdv. Just to know by this in heart. and then Gibbs used it, developed the idea in 1876, a chemical potential. Well, actually, the amount of material, amount of substance is there, dN1 and dN2. Okay, and then for each species, it has a chemical potential mu1 and mu2 in this case. So du is equal to TdS minus PdV under the condition that entropy and volume fixed. There is a chemical potential for species 1, mu1, and then amount dN1, mu2, amount dN2. Okay, so this is the kind of expression for du, which could be a potential. You see, in physics, potential is something that always the mechanical change is done from high potential to low potential. So if there is a reaction involves, that we would say that that reaction derived from high chemical potential to low chemical potential. Okay, something like that. If there is a phase change, then we say the phase change is taking place from higher potential, chemical potential to lower chemical potential. So that is the idea Gibbs developed for internal energy, but it really, and internal energy because the natural variable for the internal energy is S and V, entropy and volume, but more easier way to deal with the system is that pressure and temperature. So that is Gibbs free energy. Let's dig into it. Okay, the technique to derive those other state function is Legendre transformation. Legendre transformation is a linear change in variable to determine a new function from a known function, state function I'm saying, by subtracting one or more product of conjugated variables. Well, you see, conjugated variable is kind of, for example, for du equals TdS minus PdV. In this case, conjugated variables are T and S. Okay, those are conjugated variables. And P and V, in this case, minus P and V, those are conjugated variables. So product of conjugated variable in this case is TS or minus PV. Okay, so those are product of conjugated variables, and then you subtract it from U, a function, state function, then you will obtain another new state function. So in this case we do H equals U plus PV. So in this case the functional form is that from U, a state function, you subtract a product of minus P and V, then you just do plus PV here. So this will give you U, a state function, plus a product of conjugated variable, subtracted, then you will get another state function. How it does so, meaning is, look at this. You have H here, dH is du plus PdB plus VdP. But you have du here, you plug into this du, TdS here, minus PdB plus PdB is crossed out. What you get is TdS plus VdP. Okay, so du is TdS minus PdB with this, dH is TdS plus VdP. You see the variable, conjugated variable position changes with sign. Okay, that's what you observe here. And then the same chemical potential term. Okay, from this you can see that from this T, well, this is a differential form, exact differential form. So T is derivative of H with respect to S. So T round H round S P, and V round H round P T are of course the chemical potential. So in this case, if you have S and P constant, S and P and N constant in this case, H must be at a minimum. Okay, so what it means that if any change is done, delta H is negative because it's at equilibrium is minimum. So any change is done simultaneously, then delta H is negative. That's what it's saying. But problem here is that what need to be fixed is S, P, and Ni. P and Ni is no problem, but S is very difficult. Entropy is impossible to control. So almost impossible. Maybe I don't really exaggerate extremum, but anyhow, most of the case entropy is not really controllable anyhow. So a constant S, P, and Ni. H is a minimum, so you can use H as a criteria for kind of simultaneous process like that. So people, instead of H, people would like to have a control of certain state functions. So S could not be controlled, so people ought to choose other, which is pressure and temperature. Volume is hard to control also. So eventually we'll develop a state function, which is the function of pressure and volume, pressure and temperature only. Before we do that, we do the Helmholtz free energy. So we define A from internal energy by subtracting the conjugated variables T and S. So du equal TdS minus PdV. So T and S are conjugated variables. So we subtract from U the product TS. Then dA is equal to du minus TdS minus SDT, but du is TdS minus PdV. So TdS is cancelled, and then minus SDT minus PdV. Okay, so that's dA. So in this case, A, when T and V constant, which is much easier than S constant, then which is in the minimum. Okay, so if any change when temperature and volume fixed, then if any change is simultaneous or happens, then you must have delta A negative, less than 0. Equals 0, which means that you are in equilibrium. And now also there is the equation of state. S is minus round A round T, P equal minus round A round V, just like this. Okay, so equation of state is a relationship among state functions. Okay, so S and A and T relationship. So this is the equation of state. So finally, we are going to derive the last state function we need to have to, at the at the beginning of thermodynamics is U and G, U to G, Legendre transformation. Now what we do is that from U we subtract minus PB and subtract TS. Actually, U plus PB is H, and then it's also equivalent to H minus TS. Okay, du is TdS minus PdV, which is the fundamental equation. dg is equal to du plus PdV plus VdP from here, and minus TdS minus SDT from here. Yes, and then du is TdS minus PdV. So minus PdV cancels this, TdS cancels this. What you get is minus TdS plus VdP. So S is round G round T minus. Okay, V is round G round P. Okay, so you just have this in mind. Okay, look closely and remember, S is round GT, V is round G round P. Okay, and then when T and P and N constant, G is at its minimum. So that's the criteria. If process happens, then delta G or dG is negative when T and P are constant. But T and P constant is kind of very convenient or easy to accomplish in normal laboratory setup. Temperature fixed, and then pressure is normally not changing much, so it's fixed. So that is the normal condition, or kind of easy condition to maintain. Okay, so we now have all state functions ready to use, and then we are going to develop some idea how to utilize these state functions for our work. Basically what we are doing is that there are measurable quantity, measurable state functions, and then we use those measurable state functions, the value of the state function, to calculate other state functions. Okay, so that's basically the idea. So temperature, let's first do the temperature effect of Gibbs free energy or Gibbs energy. Remember that round G round T was minus S, and then which is negative because S is always positive. Okay, and then what you do here is that G equals to H minus TS, and then S is here, so H minus T round G round T. Okay, so this is the relationship we obtain from just directly from this. And then what we are going to do is we are doing the temperature derivative of G over T. So what you do is that keep G and then make a derivative of 1 over T against T. So first one is to keep G the same, G the unchanged, and then 1 over T derivative is minus T square, 1 over T square, so negative G over T square, and then keep 1 over T and then make a derivative of G. So 1 over T is here, derivative round G round T. Okay, so this is minus S. Okay, so what you have is that, I'm not good at this, but let me use the pen just like this. Okay, I'm not sure I can do that. So basically what you have here is equal to minus, okay, T square over G, and then plus, I'm sorry, so this is term, and that term, I guess I have to use this one. Still don't give me this. Okay, I got. Okay, this is minus S. So what I have is plus, just like this. Then this one is negative. I would have T square. Then what we have here, G. And this is negative and negative, so I need a negative and TS. So what do I have is the G minus TS. H is G equal H minus TS, so minus minus plus, minus minus plus. Yeah. Oops. What do I here is minus, and that is negative here. Yeah, I'm sorry, that's something. I got it. So minus again. Okay, this one is here, and then this is negative. I'm sorry, so it's negative 1 over, just like this. So what we have here is that negative T square G plus TS. Then this is what? This is H. So what we have, why we are ending is like this. Okay, so this is it. And then H is minus T square times this one. So minus T square times this one. Well, this is the relationship. The name is the Gibbs-Helmholtz equation. So this is the Gibbs-Helmholtz equation. And if we put the delta here, then we put the delta here. So this is the Gibbs-Helmholtz equation. Okay. So you just keep this in mind. And this is very important in a way that this is a open window to statistical mechanics, kind of easy way. Okay. So this is important. Okay. So nextly, temperature effect and then pressure effect on Gibbs energy. So round P equals B, which is also greater than 0 because B is, there is no negative volume. So integrate dg is that integrate V dp. Okay, so this is basically the relationship from G1 to G2, P1 to P2. So G2 equals G1 plus round integral P1 to P2 VdP. And this V is constant in this pressure range from P1 to P2, then we can do this way. G2 equals to G1 plus V, because which is considered to be a constant from P1 to P2, then this is the relationship. And mostly for the liquid or solid, which holds, that's the relationship. But for the gas, and then we are going to talk about ideal gas in this case. So V equal nRT over P. So V here is nRT over P. Then integral G1 to G2. In this case, G1 is a kind of reference state to the current state. So integral G0 to G dg, which is G0 minus dg, and then G equals G0 in this case. And then nRT is here, and then nRT are all constant against P, but what you have is P0 to P. What you have is P0 to P. P0 to P is dp over P, and that is dLnP. Okay, so that is dLnP, and then dLnP is integrated to ln P0 P to P over P0. Okay, so delta G equals G2 minus G1 nRT ln P2 over P1. So this is the relationship. Well, this relationship is used to define the Gibbs free energy. The molar Gibbs free energy. Gibbs free energy per mole is chemical potential. So chemical potential in terms of a state function, chemical potential is expressed by an activity. Activity is a kind of effect of that substance, okay, for the state. Okay, so that's basically what is the idea. What's the idea is behind the activity. Okay, so next thing we are going to talk about activity. So we have this relationship, G equals G0, the standard state Gibbs free energy plus nRT ln P over P0. Well, the reason for this is important is that per mole n equals 1, then this is mu and that is mu naught. If it's a mixture, there are species 1, 2, 3, 4 like that. So mu I is the chemical potential for the ice substance, ice component, I would say. So mu naught equals mu I equals mu I naught, and then n is 1 RT n ln AI. So this is we kind of consider this is a AI for a mixture. So AI is a activity, but we just kind of look more into the idea what is behind for the activity. So if I equals 1, then mu I is equal to mu I naught, which is the reference state chemical potential. So for the reference state, AI equals 1. Okay, so reference state. What we are going to talk about reference state is. So for the ideal gas, reference state is pressure itself. partial pressure itself. So for the ideal gas, reference pressure is that whatever it is, its own pressure. That's the ratio of it. So that's AI. Well, actually, for the ideal gas, the reference pressure is 1 atm, or for the SI unit, which is 1 bar. So actually, the reference state is 1 bar, then whatever pressure it is, some bar, then activity itself is unitless quantity. So that is, so for an ideal gas is defined by reference pressure, its own partial pressure ratio to the reference pressure. For the real gas, the partial pressure is expressed by with a fugacity. So fugacity is a kind of effective pressure of that real gas. Consider that to be against the amount of pressure of ideal gas at that position. Okay, so real gas activity is that Fi fugacity over the reference state, reference pressure. And for a solution, which is the molality, ideal solution, then is 1 molar solution is that is standard state. Then real solutions case that we multiply its molality with the activity coefficient gamma I. So that's the activity for the solution. And for pure liquid or pure solid, we define the activity of pure solid or pure liquid, activity 1. That's why you don't include the concentration of pure liquid or pure solid in your equilibrium constant. Okay, so that's why so that's basically we just looked over what the activities are. Activities basically express the chemical potential in terms of its concentration, its pressure, or its kind of activity. Okay, yeah. Okay, so we have 4 energies: internal energy, constant pressure energy, which is enthalpy, and then Helmholtz free energy and Gibbs free energy, volume constant free energy, and pressure constant free energy. Okay, and then S and V are natural variables of U. P and S are natural variables of P. You see, natural variable of internal energy and enthalpy, there is a S, which is uncontrollable, so not easy to control. So this is rather difficult to handle. That's why we develop free energies, which have internal natural variable T instead of S. Okay, so for A, the natural variable of Helmholtz free energy is T and V. Natural variable of Gibbs free energy is T and P. Then we express du equals TdS minus PdV, dH equals to TdS minus plus VdP, dA equals minus SDT minus PdV, dG minus SDT plus PdV, now VdP. Then you see the Euler, these are all exact differential, so that you derive the Euler criterion, meaning is that you derive T with respect to V, which is equal to derive minus P with respect to S. Okay, dt round T round V S equals minus round P round S V. So this is the Maxwell relationship. All are the same in a way. You see, well, there is a old trick to remember this, but anyhow, you just know this from this. But you see, like a photographic memory. You just look at this and then memorize it, and then you utilize this idea many times in driving thermodynamic relationship. Thermodynamic relationship is always we have thermodynamic quantity measured, like T, temperature, volume, pressure, like that, and then we use this quantity to evaluate thermodynamic functions that we cannot measure, like entropy or activity, activity maybe, which just gives free energy in this case. Okay, so there are some examples we are going to do that. Those are very fundamental. So you just all those I've been talking about are subject to memorize by yourself. Okay, so this is one of the example. Heat capacity dq round u round t v dt. So this is cv actually. P external round u round v t dv. So when volume constant, this is this one, and then dq is cv dt. So dq is cv dt in this case, volume constant, but pressure constant instead. Then P external is P, and then dqp is cv dt plus this term. Okay, but with P instead, P external. Okay. So, but if you divide by dt both sides, then dqp dt is what? Cp. And then Cv is in this side, but to the left hand side it goes with negative sign. And then what you are left to on the right hand side is P round u round Vt dv dt at P. Okay, so this is the relationship of Cp and Cv. And the first term here, P times round u around V round T, is that when you increase 1 degree or unit temperature, there is volume increase. Then that's delta V times P, which is the work. So work, this is the work produced per unit increase in temperature at constant pressure. So it's a kind of real, if you increase the volume, if you increase the temperature, then increase the volume, that works. That is P round V round T, P term. Okay, so this is the work. And then the second one, round U round Vt round V round Tp. In this case, you increase the temperature and increase the volume. But per volume increase, the energy change. Volume increase, then it increased the average distance among molecules, and then it reduced the interaction. Okay, so energy per unit temperature required to separate molecule, okay, against their intermolecular attraction. That's the interpretation for this one, and then we call this as internal energy. Internal pressure. Internal pressure, okay, because this is corresponding to pressure concept. But ideal gas, for ideal gas, they do not interact. So they do not interact, so it doesn't matter how far it apart, okay, they do not interact. So for the ideal gas, this internal pressure is equal to 0. And then for the ideal gas, round V round T is V equals what? nRT over P. So temperature derivative is nR over P. Okay, so this is for an ideal gas, this is 0, so you don't need that. And this is nR over P, and you multiply P with that, and then P cancels, so nR. So Cp minus Cv is equal to nR. So this is the relationship. Well, actually, this is kind of exam item. So many times we used it, probably not anymore. So that's what we know. Okay, that's the ideal gas case. And then what you have is real gas. So what is the internal pressure of real gas? Round U round Vt equals T. What happened is, this is round U. du equal Ts minus Pdv. Okay, again, we'll give you this one. It's much easier because I'm using my mouse, and then it's not so easy to handle. T ds minus P dv. V, but molar quantity, for molar quantity we have an overbar like that. So basically what we're doing is that using dV we just do this one, and then you don't have it here. Okay, so round U round VT equal T round S round VT, and minus P dV over dV is cancelled. So we are now up to here. Okay, good. Now what? And then this one goes to round P round T V. Why? You see, this is the Maxwell relationship. I should have not erased this. The fundamental equation. You see, fundamental equations round S round B is equal to what? Round P round T. Okay, see the cross derivative and negative. Okay, so negative is positive. So this one. So you replace. The same. Replace this with this. That is from Maxwell relationship, and then negative P is the same here. Okay, so Van der Waals gas P equals to RT over B bar minus P minus A over B bar square. Okay, so this is form of gas. So round U round VT is, we are doing this one, T times round P round T. So P times round P round T is the round P is the, this is 0, round P round T is R over V minus P, but there is a P multiplied, so RT recovered, minus P is here, so minus P is this one, so this minus this, and minus plus, you obtain this one. So round U round VT for Van der Waals gas is A over V square. Okay, so this is kind of for the attraction. So that's the internal pressure. Okay, for the ideal gas this was 0. Just remember that. So this is one relationship we looked upon, and then this is the last one. Well, basically what we are talking about here is that we measure physical quantities, and then there are measurable state functions. Those are basically temperature, pressure, volume, and these two. Cubic expansion coefficient and isothermal compressibility. Cubic expansion coefficient is that relative expansion with respect to increase in temperature. Okay, so which is defined in 1 over V round V round T P. Okay, so if that's 1 mole, for 1 mole, then 1 over V bar round D bar round T P. And also, well, actually there must be here must be 1 over V2. Okay, round V. This is the volume increase in unit pressure change. Okay, so that's isothermal compressibility because T fixed. That's cubic expansion coefficient, isothermal compressibility. So that's the idea. And then with that, and also we have cyclic rule. You see cyclic rule among PTV. So round P round T V equals this ratio, and this one we put both 1 over V denominator and numerator. We have alpha here and kappa in the denominator. Okay, so this is kappa over, alpha over kappa. And why we need this is that you remember that round U round VT equals T round S round VT minus P, which is equal to, we just did that before, a couple of slides ago. Round P round T. This quantity is actually alpha over kappa. Alpha and kappa are measurable quantity. So this is then minus P here. So alpha T over kappa minus P. Well, actually this is it. Alpha T over kappa minus P. And Cp minus Cv is this quantity, and that is P plus alpha T over kappa minus P. So this total quantity is alpha T over kappa, and this is what? This is V alpha. So alpha T over kappa times V alpha, which is TV alpha square over kappa. So Cp minus Cv in general, not only for ideal gas, is that T and V measurable, alpha measurable, because this V and T is only the variable here, and kappa, V and P are only the variable here. Kappa also measurable. So Cp minus Cv is expressed in terms of all measurable state functions, state quantities. Okay, so basically that's what we are doing. We develop the relationship among those state functions, and then what we cannot measure, we obtain those from measurable state functions. That's what we do basically in thermodynamics. So keep practice it. Before I finish, and then I just tell you, make your own note out of this lecture, and then memorize it, and then then apply this to your problem solving, and then practice, and then you get the really permanent idea, real firm grasp of thermodynamic ideas. Okay, thank you.